Caroline, could you just remind everyone to ask questions, primarily through Slack, if they can?
Okay, yes, I will remind everyone. Okay, so welcome everyone. We should be streaming on YouTube already, and I think it's 1500 GMT now. So let's slowly get started while people keep dropping in. And well, yeah, just to welcome you again to the last session of today, which will be the second session actually on analytical and numerical modeling of the 21 centimeter signal. And we will start off with an invited talk. That's a 30-minute slot, and followed by a break. And then we have further contributed talks. And I would like to just remind you about the timing that for the 30-minute invited talk, I will give a 5-minute warning if this is okay. And also optional to have some time for questions then, of course. And then for the contributed talks, I will give a 3-minute warning for the 15-minute time slots. And well, as a second reminder, also, so please feel free to post lots of questions now. And also, of course, if you watch it later, you can still post them on Slack. And also during the talks now, we encourage you to post them on Slack and well, to keep the discussion going there. If you have trouble with that, of course, you can also post it, for example, here on the Zoom. So yeah, whatever channel, of course, is best for you. So let's get started. We will open the session with the invited talk by Alkistis Pourtsidou from University of Edinburgh, talking about the 21 centimeter intensity mapping from Pathfinder data analysis to future series preparation. So please share your slides. Yes, perfect.
Okay, I guess you can hear me okay. So yeah, thanks a lot for the invitation. I'm going to give a general overview, I guess, of low redshift 21 centimeter intensity mapping with a focus on modeling challenges and with a focus on recent progress on H1 constraints from Pathfinder experiments. So I don't need really to introduce to this audience what intensity mapping is, but it's always good, I think, to put things into context. So what we are used to in cosmology when we have large surveys, these are usually optical galaxy surveys, where basically the final data product is a catalog of galaxies with array and deck coordinates and redshifts, ideally spectroscopic redshifts. This is extremely expensive, but surveys like SDSS, BOSS, EBOSS, etc. have already done it. Surveys like DESI and Euclid will do it even better, and it's a fantastic way to do cosmology. But it's extremely expensive, and it is almost impossible in the radio unless you have a very futuristic galaxy survey with something like SKA phase 2. With smaller things like Meerkat and SKA phase 1, you really, the arrays are sparse and they don't have enough sensitivity, to detect with confidence the tens of millions of galaxies you need in a large area of the sky to do cosmology. What you want to do is, instead of using them as interferometers, you want to use them in the so-called single disk mode. So literally use them as a collection of single disks that can scan the sky very, very fast, and use intensity mapping, take the integrated flux, all the photons from many galaxies together in large three-dimensional pixels on the sky, and then you have a map, and you have lost some of your angular resolution, but you still have excellent redshift resolution, and you retain the large scales you need to do cosmology. Of course, there are also purpose-built interferometers, and we have heard already in this conference great talks about them. People talked about Chime, Hyrax, Chord, and other instruments, and yeah, they are all fantastic. Personally, I have been working mostly on single disk experiments, so some of the talk is focused on that, but most of the things I will say, I think, concerning the modeling are applicable everywhere, and also relevant to Epoch of Reionization experiments, not only low redshift. So just to remind ourselves, why do we want to do this? We have optical galaxy surveys, but these can become short noise limited. Neutral hydrogen intensity mapping is not, and opening a new observational window to the universe is always good. So it would be really fantastic if we can do precision cosmology and galaxy evolution studies using radio observations. And in the previous slide, I showed the maps, the intensity maps, and these maps contain a lot of cosmological and astrophysical information. But basically what we do, we don't really work with the maps themselves. We take the maps and we extract statistics, 2-point statistics like the power spectrum from them, and then we use our models, we feed our models, and we constrain physics and astrophysics. So, for example, this very nice plot by Pourtsidou, you just see how the power spectrum is such a powerful probe of exotic dark energy and gravity theories. The better you measure the power spectrum, the better you will be able to put constraints on modified gravity, dark energy, inflation, and all the rest. Now, the fantastic thing about intensity mapping is that you can do all the usual stuff in principle that optical galaxy surveys do, like constrain dark energy, but you can also constrain really well neutral hydrogen parameters, like the H1 abundance, omega H1, and the H1 bias, BH1. These things are important. They are very important for galaxy evolution, which is still, largely unconstrained. There are several mysteries to be solved. So if you manage to really understand how the H1 abundance evolves with redshift, you can put, you can make the strangest tests of galaxy formation and evolution models. So that's really great. So here is a very simple plot of what the power spectrum, the cross-correlation power spectrum of an SKA intensity mapping survey times Euclid, across something like 10,000 degrees on the sky at redshift equals 1 will look. And if you ignore complications like redshift space distortions and things like that, you can simply write this power spectrum, this cross-correlation power spectrum, as the product of the underlying matter power spectrum, because neutral hydrogen is a tracer of this underlying matter power spectrum, times an amplitude that is defined by this H1 abundance, which you want to constrain, the H1 bias that you also want to constrain, the galaxy bias that you can just take from your galaxy surveys, and this R coefficient, which basically tells you how H1 and the optical galaxy sample are related. So basically this tells you about the H1 content of different galaxy samples, which is a very unique and clever thing that you can do in high redshift. By high here, I mean redshift 1, redshift 2, etc. By cross-correlating intensity mapping and galaxy surveys. And if you do that, you can basically populate this diagram here and really understand with intensity mapping how H1 evolves across basically the whole redshift range until reionization kicks in. So this diagram contains some, not all of them, but some of the most important H1 constraints we have via other means, either in the very local universe from H1 galaxy service like HiPass, or at the late time redshifts 2, 3, 4 from DLA systems. So these constraints are derived. You can see that while the redshift range in this diagram in the x-axis is really huge, it almost covers 12.8 billion years, we really do not have enough measurements. So, and most of the measurements that we have really, big error bars. So we would really like to populate this diagram in a much better, much more efficient way, and really pin down how neutral hydrogen evolves from redshift 6 to today. And intensity mapping can really do that. So with intensity mapping, we can really greatly improve on these H1 constraints and populate this diagram. And of course, forecasts like the ones I present here are very optimistic in the sense that we have ignored various systematics, but we do know that cross correlations with optical galaxy surveys, for example, helps a lot and really allows us to constrain this H1 abundance and the H1 bias. So here I only show constraints assuming large-scale surveys with SKA mid and near-cut and SKA low, but of course the redshift range from 1 to 2.5 is also covered by CHIME, HIRAX, will be covered by CHORD, etc. So in my opinion, this is one of the best things that intensity mapping can do. And the modeling requirements for this are not so stringent as when you want to do cosmology. Now, if we move towards actually doing cosmology, we definitely need simulations. We do know that optical galaxy surveys have only really reached their full potential when they had simulations that they could trust. And this includes simulations of the signal, but also simulations of the, of observational effects. So some work that I have been doing with Steve, Paula, and Catherine is, taking basically simulated data products that our optical galaxy friends have made. This includes n-body simulations, populated with halos, and even halos populated with galaxies, and galaxies populated with H1, and just doing the easy thing of taking these amazing data products and turning them into 21 centimeter intensity maps, which includes sometimes using a semi-analytical model to go directly from halo to 21 centimeter, and then just smoothing the map with the beam of the telescope. And then when you have your signal map, you just add the noise of the experiment that you are interested in. And then you also add simulated foregrounds, because we do know that the signal is buried under orders of magnitude larger foregrounds. These foregrounds, again, I don't have to introduce this to this audience, but and people have already talked about them. These foregrounds are mainly galactic synchrotron, extragalactic point sources, extragalactic free emission, and galactic free emission. And the biggest problem is probably that there is an interplay between some of these foregrounds, at least, and the instrument, which can distort their spectral smoothness and make their removal a bit more difficult. So one thing that we have been working on is dealing, basically comparing foreground removal techniques and then dealing with the inevitable signal loss that you get on large scales, especially. That other people have already mentioned that as well. So I want to talk a bit about that in terms of how to deal with it at the modeling level and what observables we can possibly repurpose to identify systematic behavior. So here I saw a very simple example where we take some simulations that should correspond to a meerkat or an SKA-like experiment. The first panel on the top is just H1 plus noise. Then you add foregrounds and you see how the map's appearance and the amplitude of the temperature changes by orders of magnitude. And then you clean it. And you see that, you're cleaning, we have used principal component analysis here, but we could also use, Gaussian processes, DMCA or whatever. The cleaning works. So you get rid of these very high amplitude, smooth components, but inevitably, you lose some signal. And that is because on the large radial scales, the foregrounds and the signal are very similar. So basically, yeah, you inevitably lose some signal. And you can see in the bottom panel here, which is the usual spherically averaged power spectrum, that the fiducial, the black line, the true signal without any foreground contamination is at a certain level, and then when you include foregrounds and then you clean them with principal component analysis, you do get a signal loss that is more evident on the large scales. So what do you do about that? I want to introduce what we think is a good way to identify not only the effects of foregrounds, but also effects of weird beams or anything else that can have an anisotropic directional dependence. And again, it is inspired by optical galaxy surveys analysis. So as many people before me have said, the observed power spectrum is obviously the redshift space power spectrum. So you have, it's anisotropic. You have the effects of redshift space distortion. There is a preferred, line of sight direction for them. So the power spectrum becomes anisotropic. So instead of working with PK mu, with all the possible PK mu's that you would have, a huge, very complicated covariance to deal with, for example, what optical galaxy surveys do is they use the basis of Legendre multiples. So they express this PK mu, they compress it to basically 3 multiples, the monopole, the quadrupole, and the hexadecapole. So the monopole corresponds to the 0th order Legendre multiple, L equals 0. And this is what we all know, it's the simple spherically averaged power spectrum. This we use a lot. But then you can have odd multiples like the dipole, which corresponds to L equals 1, and this should be 0 if everything goes well. Then you have quadrupole, L equals 2, hexadecapole, L equals 4, octupole, etc., etc. So why are these things useful? Basically, you can understand how they are useful and what they represent if you just take the simple model of linear theory. So if you just take that you have a galaxy or an H1 intensity mapping, and you have your bias, you believe you are on linear scales, so you can model the signal with linear theory. So you only have the linear matter power spectrum and the Kaiser redshift space distortions, which basically depend on the growth rate of structure, which is what ideally you want to measure if you want to, to do modified gravity and all the rest of the stuff. So since the Kaiser formula contains terms with this mu, which is the cosine of the angle between the K vector and the line of sight, only going up to mu to the 4, if you do the math, it's very simple. You will see that in linear theory, only the monopole, quadrupole, and hexadecapole are non-zero. And these are basically the multiples that optical galaxy surveys use, because even in non-linear theory, the higher order multiples are very tiny. So the signal to noise is not enough, so they don't use them. The monopole, quadrupole, and hexadecapole contain basically all of the cosmological information. So you can just do with them. Now, it's very instructive to see that in linear theory, you get an analytic expression in terms of this beta, that is basically the growth over the bias. And you immediately see that if you didn't have redshift space distortions, for example, the quadrupole, which is L equals 2, P2, and the hexadecapole, which is P4, would be 0. So the quadrupole and hexadecapole are smoking guns for redshift space distortions. This is very nice. The dipole should be identically 0. Higher order multiples should also be 0. And as I said before, even when nonlinearities and other effects like GR effects or whatever, tiny effects are taken into account, the above should approximately hold. So any extra little signatures that you get, like nonlinearities giving you higher order multiples, should be small. But this is the ideal case. When you go to intensity mapping, we do know that we have anisotropic systematic effects. For example, in single disk experiments, the effect of the beam is basically dominates the angular scales. So it is anisotropic a priori. The foreground removal signal loss dominates the radial scales. So also this is anisotropic. And this basically means that if you do the multiple expansion, if you work with monopole, hexadecapole, quadrupole, and all this stuff, your observed multiples will disagree greatly with your theoretical modeling. But the point I want to make in this talk is that we should be using this to our advantage. And basically, I want to suggest that we should be working with this kind of observables. We should be working more with this kind of observables. So the fact that your observed multiples will disagree and they will have strange features is not only a statement for single disk experiments, although these plots that I'm showing here and the simulations that we have are for single disk experiments. They are also relevant for interferometers, because in interferometry, you again have an isotropic, directionally dependent systematics, not least because of foreground removal, and for the same reasons also for Epoch of Reionization experiments. So here you see that in the fiducial case, so if we assume perfect foreground cleaning or no foregrounds at all, we have the black lines, monopole, quadrupole, and hexadecapole basically agree completely with the theoretical predictions that we have in optical galaxy surveys. But if you do have foreground removal effects, you get a reduced monopole, you get an enhanced quadrupole, and you get this crazy looking hexadecapole. So the suggestion here is that we can use multiples for hunting systematics. In fact, things like the dipole and higher order multiples, in my opinion, can help a lot, because they might not contain cosmological information at all, but they should really be 0. So we should always be checking them. And I think that the weird systematics that we have in 21 centimeter experiments will result to very big signatures in this dipole and higher order multiples. So I think they can help us a lot. Another very related observable that I wanted to show you is the clustering wedges that again have been used a lot for analysis of optical galaxy surveys. This is simply that you take the power spectrum monopole, so the monopole that we all know and love, but instead of spherically averaging to get it, you cut off certain new wedges. Here again is a study that we did on simulations. And for the different wedges, there are differences, bigger differences or smaller differences with the foreground and no foreground case. So you see here in the first wedge, the top left, where we took the 0 smaller than mu smaller than 0.25 wedge, the difference of the truth and the observed power spectrum, of the cosmological truth and the observed power spectrum, is huge, because the foreground removal effects are larger for large radial modes, which means for small k parallel modes, which means for small mu. On the contrary, if you take wedge number 4, which is mu 0.75, between 0.75 and 1, there is no effect. So So in principle, if, for example, you didn't know the foreground removal signal loss at all, you could, by doing a wedge analysis, identify that there is something weird going on here. You could identify that you have a directionally depending systematic, even if you didn't know at all what this systematic is. So I think this kind of observables can help us identify and ameliorate weird observational systematics. We used the foreground removal effects and the multiple expansion with my student Paula Soares and Steve to treat foregrounds at the modeling level. So we did a proper analysis using the monopole, the quadrupole, and hexadecapole, and we saw that the resulting constraints that we were getting, they were completely biased, completely wrong, if we didn't account for the foregrounds. And the point that we made in this work is that a simple scale cut, where you say, you know, just I ignore the very large K scales is really not enough, because the effect of the signal loss is very anisotropic, and it's along the K parallel and along the K perpendicular direction. So what we advocated for in this work is basically including a modeling for the signal loss, convolving your theory vector with this modeling, and then varying the nuisance parameters that are associated with the signal loss, in our case, 2 parameters, varying them together with your cosmological parameters and see what happens. And indeed, when we did that, we got unbiased constraints. But a simple K-cut didn't do it. I will also say that, you know, regardless of, you know, these things that we can try and do with Pathfinder data or with, you know, idealistic simulations, what we really need is end-to-end simulation. So we took in the SKA cosmology group, we took a first step on that with our blind foreground subtractions challenge. So if you missed Isabella's talk earlier, please go and see it, because this paper really shows what really happens with your foreground removal techniques, for example, if you put a bit more realistic beam in the simulations, etc. So I hope we will continue this work. And lastly, I wanted to talk about some data analysis work. So currently operating telescopes that we have are the Green Bank telescope, of course, that did the pioneering survey and the pioneering detection with the Wiggles galaxies. We have Chen that has data, and we also have Meerkat that has data. I'm not going to talk about Meerkat, even though I'm really involved in the work, because Stephen is giving a talk, I think, tomorrow, a very nice talk on with some exciting results, I think, from what we have been doing with Meerkat intensity mapping data. So stay tuned for that. I'm just going to talk about the importance of cross correlations a bit. As everyone knows, systematic effects, and I'm keeping track of time, so I think I have like 3 minutes.
5 actually.
Okay, I have 5,
yeah.
So that's good. So systematic effects are a big challenge for 21 centimeter intensity mapping, and at low redshift we are extremely lucky because we have overlap with loads and loads of optical galaxy surveys, and we should we should exploit that as much as we can until we get our autocorrelation. It can be great help to ameliorate systematics. So GPT and Wiggles, the 2013 pioneering paper by Kiyu Masui, Chu-Ching Chang, and other people showed that, even when you don't get anywhere close to an autocorrelation detection, by cross-correlating with optical, you can mitigate systematics because they drop out. And then we had the 2DF cross-parks 2018 detection, and we had our GPT and EBOS detections last year. I wanted to note here that the constraints that we get rely on transfer function correction for signal loss. This is likely fine. I just want to mention this is likely fine for Pathfinder experiments that are very noisy, and that we really have to assume that we know the cosmology and we are only after the H1 parameters, but it's not fine for the precision studies we really want to do. I think that our work and other people's work have basically shown that the transfer function is very likely, very strongly cosmology dependent. So we have to take that into account as we move forward. So the GPT data analysis is the final part of the talk that I wanted to just describe how we did the GPT cross EBOS work. So the GPT observes different sections, meaning different observing seasons, and it gets its autocorrelation by cross-correlating different seasons. This is because by cross-correlating different seasons, the noise associated with each of them is independent, so it drops out. So you can get a power spectrum without a thermal noise bias. And if you're lucky, you can also get rid of time-dependent systematics. So if you observe in different seasons, the same parts of the sky, but different, different times, if you have a strongly, time-dependent RFI or whatever, you can get rid of that as well. So GPT has 4 seasons, and you can use the auto seasons or auto sections as a proxy for the noise of your experiment, because it's quite noisy. And the cross section, as I said, should be a proxy for the H1 signal. But what happens in reality is that even if using a cross section, so section A, cross section B, for example, to get rid of your noise bias, it is true, you get rid of something, you have a lot of residual systematics in, so you end up having a power spectrum autocorrelation that is an order of magnitude larger than what theory tells you it should be. So that's a problem. So that indicates residual systematics in the data, and this is why you need to resort to cross correlations. So this is what we did. So we built upon the work of Kiyo and Zhaoting and other people in 2013, and we cross-correlated GPT data with overlapping EBOS, ELGs, and LRG samples. So EBOS is the best optical galaxy survey we currently have, and we realized that there was 100 square degrees overlap between GPT and EBOS, and basically we saw that we got detections when we cross-correlated with the ELG sample, we got detections with the LRG sample, and we also confirmed the original Wiggles detection. And we saw that this simple empirical model that is on top of the page fits observations quite well. So these are like 5 sigma detections that have a good chi-squared, and we got some nice constraints out of them. One point that I wanted to make is that as we move to hopefully more higher signal to noise data, we should move away from these empirical models that are incorrect. For example, we know that the H1 bias as well as the galaxy bias and this cross-correlation coefficient should be scale dependent and not just a redshift dependent amplitude. We did take that into account in our paper as much as we could, in the sense that we saw different results for different K ranges. So we took 3 different K ranges and we assumed these things are constant in these different K ranges. And what we got is different constraints, which basically proves what we already knew, that these things are intrinsically scale dependent. So we really need better modeling, but fortunately, we do have better modeling. I'm sure that, perturbation theory will work as well as it does for optical galaxy surveys, and halo models will also work well. What we need to improve a lot is our simulations, make them end-to-end, and improve things like foreground signal loss modeling and systematics, hunting for systematics.
I'm sorry, I think we're over time already. I'm sorry. Okay. I think we need to wrap up for the break.
Yeah, that's my last slide. I just wanted to say that even with this very difficult and low signal to noise data, we did manage to populate this diagram at a redshift 0.8. So I think the future is looking bright for intensity mapping.
Okay, thank you. That's a good positive note to finish the overview talk. So thank you very much for this nice overview. We a little bit over time for the break. If there's a quick question, maybe we can have this, but please also feel free to not be first. I have one in the question A here. I think Slack was still empty, but please post also on Slack. Why does the amplitude omega cross bias cross R decrease at small scales? Is there a quick
this is,
answer?
yes, I should answer in Slack. Are you in Slack, Mona? It's not at small scales, it's the different ranges that we took. It's because of the scale dependence, basically. But so if you knew the scale dependence of the bias and R, which you do not know, you should get the same omega, that's for sure. So omega should only be a function of Z, it's the global H1 abundance. We do know that bias and R are scale dependent. And maybe I can give you more information in the Slack about what exactly we did with simulations in the different scales, and we can talk. But for sure, if you are confident about the K dependence of the bias and the R, you should get the same omega. You should not get a decreased omega, no matter the scale you are using.
Okay, yes, thank you very much. So I think, yeah, this is probably something nice to continue discussing on the Slack. So thank you very much again. And for all the attendance, I'm sorry for the slightly shorter break, but I hope I am sorry. No. I think the interesting talk was worth it. And if it's okay, I would ask everybody to come back in 10 minutes for the rest of the session. So see you then. Thank you.
Thank you. Bye.
Hey, yeah, so Ivo, if you want to, you can already share the slides. But
Okay, you can still hear me, right? I do worry sometimes with Zoom. Hello?
I think everything's fine, Eva.
Okay, I've had some Zoom connections before, Zoom connection issues before. Just tell me when you want me to start, I don't mind.
okay, yeah, I see the slides. Let's maybe wait, yeah, like a good minute and then.
Yeah, no worries.
Thanks. Okay, so I guess we can get started with our session second part with contributed talks. And our first speaker is going to be Ivo Georgiev from Stockholm University. And yeah, the floor is yours.
Hi, well, my name is Ivelin, or Ivo Georgiev. I'm a PhD student at Stockholm University. Thank you for giving me the chance to present for this conference, and thank you to all the participants and speakers for all these interesting talks. The talk I want to contribute to this discussion is the impact of the mean free path parameter effect on the large-scale 21 centimeter power spectrum from the Epoch of Reionization. I wanted to give a quick content and overview, what I'll quickly cover. And the first thing I do is I decompose the 21 centimeter power spectrum into the density field and the neutral hydrogen fields, and I study their evolution. I then look at the mean free path of ionizing photons during reionization and simulations, that is. And then I study the mean free path effect on the shape of the 21 centimeter power spectrum. This is a very specialized group, so most of you know a lot about the Epoch of Reionization, and it was discussed a lot in the previous sessions, but the main point I wanted to give with this picture is that the Epoch of Reionization spans both astrophysical and cosmological scales, from the first stars to the IGM, and then the 21 centimeter signal, and thus the 21 centimeter power spectrum, contains information on deionization and density fields. So one question one could ask as a motivation and aims of this talk and the paper that I have been writing is which K-scales of the 21 centimeter power spectrum contain cosmological information. And one way to try and understand this is to decompose the large-scale 21 centimeter power spectrum and then investigate a bias parameter. And a possible motivation might be that radio interferometers are well attuned to studying low scales, or at least the low scales I define, and low scales should be easier to understand. That is to say, low K-scales. So the first thing I do is I take this decomposition from Litz et al. 2007, and I apply it on large scales, which I've defined as follows. One way to try and understand the evolution of this formula, of course, it has many components, is to divide each of these terms against the 21 centimeter power spectrum on the left-hand side. And then I study the fractional contribution of each of them throughout the Epoch of Reionization. So from a neutral fraction of 1 to 0 when reionization is complete, and this is particularly for a fixed K-scale. So you can imagine which of the terms contributes the most in constructing this part of the equation. And positive contributions are in solid, while negative contributions are in dashed. Essentially, what you can get from this figure is the following: that at least early on, within the first 10% of global ionization of the universe, the 21 centimeter power spectrum depends on the cosmological density power spectrum, after which is determined by the power spectrum of neutral hydrogen. Higher order terms, the one you see in yellow, orange, and pink, play less of a significant role throughout reionization, but they're still important in some specific areas that I'm showing right now, but are essential in determining the shape and well, not the shape, but the amplitude of the power spectrum. And the cross term seems to play an important role from start to finish. But essentially, it's between these two. So one could argue that if you take the 21 centimeter power spectrum, let's say at the midpoint of reionization, as I've done in this figure, we should be able to understand the 21 centimeter power spectrum simply through the power spectrum of the neutral hydrogen. However, we see that at large scales, the 21 centimeter power spectrum is a biased version of the cosmic density power spectrum. And one question that one could ask is, how does this happen? And at which point does the 21 centimeter power spectrum transition away from being a biased version of the density power spectrum? And this is quite often in the literature related to this characteristic feature, which has often been associated with the characteristic size of ionized bubbles during the epoch of reionization, or possibly connected to the mean free path of ionizing photons. And hence why I choose to then examine the mean free path itself. So I think Idon Chu discussed the mean free path of ionizing photons very well earlier in one of these sessions, but I will still give you a brief overview in case you were not there, but I do encourage you to look. So I can define the mean free path as the average distance an ionizing photons travels through the IGM. I've provided this picture of Keating et al. 2015 to give you a visual example. We can determine the mean free path of ionizing photons in maybe two possible ways in terms of simulations. In one case A is probably set by the size of large neutral islands, so ionization travels from the source to the edge of the bubble where it's absorbed by large neutral islands, or in case B, seen in red, it travels and is then absorbed by a neutral gas which still remains within the ionized region. What's interesting with this is that large-scale simulations, which I look at particularly, are very coarse, so cells cannot always actually resolve the small-scale feature and accurately model the mean free path due to case B. So quite often what's applied in the literature is a hard barrier to ionizing radiation, maybe similar to A, where the ionized bubble is not allowed to travel any further. Conversely, the mean free path in terms of observations is a very interesting quantity which is very actively discussed right now. Determined from quasi-stellar objects, we can see that previous measurements of the mean free path give one interpolated value of what it should be at redshift 6, but present work suggests very different results by a factor of 10. So it's sort of what you should take from this is that the mean free path seems to be very essential in the epoch of reionization, but also as we see how we model the mean free path will be very important in simulations of reionization. So in order to do this, I study two sets of simulations using the C2Ray code, a size 714 co-moving megaparsec. The first set of simulations uses a hard barrier, and I've applied two different values of the mean free path, one 19 co-moving megaparsecs, so not too dissimilar to the Becker et al. 2021 measurement, and the model in purple has a mean free path hard barrier value of 70 co-moving megaparsecs. So that's not too dissimilar from the interpolated value. On the other hand, for the other set of models, I fixed the mean free path value to 10 co-moving megaparsecs, but instead I varied the mean free path effect itself. So the red model uses a hard spherical barrier, so not too dissimilar for the hard cubic barrier, but the yellow model uses a gradual absorption barrier. In this case, at the mean free path value, 10 co-moving megaparsec, the optical depth is set to 1. So I need to study this in some way, and as many of the speakers have discussed before, I also tried to make a bias parameter in order to study its evolution. If what I understand before is true, and the large-scale 21 centimeter power spectrum is a biased version of the density, the cosmologic density power spectrum on large scales, it should be scale independent, and a linear bias should be sufficient, so I can study how this evolves and where this assumption breaks down. And this is essentially what you need to take from this picture. And then if I start looking at the results and look at the first two models, that is the models that both have hard barriers of the mean free path effect, but the value is different, so 19 megaparsecs in blue and 70 megaparsecs in purple. We can see the following figure. So the bias parameter has a scale-independent regime in all of these cases and a scale-dependent regime. And how the transition between these two happens is quite interesting. Early on, there is little difference between the two models, as the bubbles have not had time to grow, and possibly the transition is set by the characteristic size of the ionized bubbles. Later on, the scale-independent regime is shifted to lower case scales, so larger physical scales, and some differences start to occur. But I'll focus on the late period where the differences are most visible and pronounced. The scale-independent regime for the model with the larger mean free path value is shifted to lower case scales compared to the blue model. And one can think about it in the following way. For the blue model, regions larger than 19 co-moving megaparsecs cannot form, but they do form because they overlap. However, the exact same happens for the purple model, but now you also have excess ionization, which can further propagate an ionized neutral hydrogen within the simulation. This transition feature, if we try to use this empirical formula, seems to be related to the mean free path. And if I do the same test, but instead I look at the two models where I fix the mean free path value to 10 co-moving megaparsecs, but I vary the mean free path effect itself, that is to say a hard spherical barrier for the red model and a gradual absorption barrier for the yellow model, we can see something similar and yet different happen initially. And then even though the mean free path is set to the same value, there is a difference between the two models. I think we can understand it in the following way, that is to say the soft barrier at the mean free path value of 10 co-moving megaparsecs has a tau of 1. So e to the power of minus tau is close to 0.36. So maybe you could argue that 36% of the radiation that has approached that value is then allowed to propagate further. So later on, there's a lot more sources that are already hitting this constraint, and excess ionization can travel further. But most importantly, the flat shape still remains. The transition is still related to the mean free path, but is now much smoother. I was probably much faster, but I would also like to just conclude this and give you the main points that you should take from this talk. So after 10% of the global ionization, the 21 centimeter power spectrum follows the neutral hydrogen power spectrum, which beyond the transition scale is a biased version of the density power spectrum. And this transition point of the mean free path value, depending on the cases, seems to be determined by this approximate empirical formula. However, the shape of the transition can vary depending on the mean free path effect. And lastly, if we take the value of the mean free path from the Becker measurements, we could use this empirical formula to derive the following relation and possibly state that scales smaller than 0.38 inverse megaparsec could be used to follow the cosmological matter power spectrum in some way. I hope this wasn't too fast, and I thank you for giving me this platform. You can hear me, right?
Yeah. So thank you very much, even for the talk. Actually, perfect 12 minutes. So we have 3 minutes for questions. And I see Zhaoting already has his hands up, and I think on Slack, sorry, was posing a question.
Yeah,
so please.
So if you don't mind, I'll just ask here. I'm wondering if it's possible to single out certain components in your power spectrum. For example, I imagine for cross-correlation between your H1 density field and your matter density field, you can binarize an image and cross-correlate that binarized image with the original image. Can that help you single out certain component, or is there a better way to do this? Or do you have to just use the brightness temperature power spectrum?
No, I think maybe it could be applied in some way. I'm now looking in further into actually studying the shape of the bias itself, and how I can deduce properties from it. So it would be interesting to follow up. I'll have to think about it though. Feel free to discuss it with me later.
Cool. Yeah.
Super.
We can dissect. We can take that to Slack. Yeah.
Okay, thanks. So we have a second question actually on Slack by Stefan Harwich. I will just read it to you. Is the mean free path a weighted average of the mean free paths of photons of different energies, since higher energy photons will have a longer mean free path? And if so, how does it depend on the SED of the sources of ionizing radiation?
I also have to think about this a bit further, but I think C2 ray is actually a multi-frequency and accounts for this, but in this case it accounts only for the ionizing photons. And I think the sources are... Yeah, I actually have to sit down and think and look a bit at the code. But thank you for the question.
Okay, great. So yeah, the questions are both on Slack as well. So yeah, you can
super.
Continue discussing
Should I stop
there.
the share?
Yeah, please, if you could stop. And then we switch over actually to Zhaoting Chen for our second talk. Yes. Okay, perfect. Yeah. It's full screen. So yeah, please, floor is yours.
Yeah, cool. Hi, everyone. I'm Zhaoting. I'm a PhD student at the Jodrell Center for Astrophysics. And today I want to talk about interferometric intensity mapping in low redshift universe. So I imagine at this point, everyone is sick and tired of the intro, but just to provide a sort of a different perspective, which is that interferometry at really low redshift, that is redshift below 2, measures very different cosmological signals. So we believe that in these redshifts that your cosmic H1 will be mainly in star-forming galaxies inside halos. So by using these arc-minute, arc-second scale measurement, you're really trying to probe the astrophysics of H1 inside the dark matter halo. So that's very different from, say, a single dish or EOR experiment at higher redshifts. But in terms of using interferometer to measure the power spectrum, we have already been briefed on the story. Essentially, the measured interferometric visibility is somewhat a 2D Fourier mode of your H1 distribution. So what you then do is you transform along the frequency axis to this cylindrical K-space. Because your foreground is smooth, so most of the foreground power is going to be inside this low K-parallel region, whereas your H1 is discrete in different frequency channels, so it will mainly occupy this, leaving you a so-called observation window. This is really sort of a well-developed formalism by EOR people. They have done tremendous work, amazing work on this, but it has not been studied in detail in terms of low redshift. So what we want to do is just to answer a set of basic questions, which is that, well, for these low redshift, is there actually an observation window? And if so, how large is it? Because, you know, idealistically, you will always have this sort of window, but in reality, it always depends on multiple things, your foreground signal, the contamination, the instrument, the frequency resolution, blah, blah, blah. So we want to answer that. And depending on if there's an observation window or not, that actually sort of determines your strategy to measure the H1 power spectrum. Because, for example, for Hera, if you have an observation window, what you can do is you just do a delay transform and you use a quadratic estimator for complicated stuff to get the power spectrum and the error bar. But however, for example, for LOFA, perhaps the best thing to do is actually to first do a map making. And you make the map and you try to do some foreground removal, do some calibration, do some foreground removal, and then you can measure your H1 power spectrum. So spoiler alert, we find that for low redshift, there actually is an observation window. So then the question becomes, okay, is the contamination negligible enough for you to just do some sort of simple avoidance? Or is it actually somewhat of a concern that you actually need to actively mitigate it? So when we talk about mitigating foreground, basically it's about trying to model its covariance. right? For example, for this MWA work, people try to explicitly model the foreground covariance by modeling different components, whereas, for example, for this Hera work, they use Gaussian process regression to try to sort of construct the foreground covariance in a more general way. So in order to answer these basic questions, it seems clear that we need to build an end-to-end simulation pipeline for these sort of redshifts, and with typical instruments that are going to target these redshifts, which are mainly conventional dish arrays interferometers, such as Meerkat and future SK-NIT. So here we focus on using Meerkat configuration to simulate 220 frequency channels, which is a very narrow redshift range. And then we put in all the usual stuff. We try to model our foreground as accurately as possible using real data. We build a log-normal H1 galaxy simulation tool that generates H1 galaxy catalogs with different realizations. And we can use these sorts of realizations to validate our power spectrum estimation pipeline to try to go to different halo model of H1 galaxies to try to explore its detectability. And finally, after you construct all these sky model, you choose an observation strategy, you specify what the telescope looks like. So here we follow a typical sort of MIGHTY specification. Here we simulate a 11.2 hour tracking of the cosmos field, which is something that MIGHTY does using Meerkat. So I'm going to ignore sort of all the technical details of power spectrum estimation and all that stuff. I want to just quite quickly highlight that we really try to build this simulation tool to be sort of as lightweight as possible in some sense, so that it, even though it's huge data volume and like a realistic observation, it can still be run, especially the power spectrum estimation can still be run on a personal computer. The way we do that is to avoid any sort of computationally expensive deconvolution, such as deconvolving the W projection kernel or deconvolving the primary beam attenuation. And this is done by using this conversion matrix. So you have the usual quadratic estimator that you do to compute the visibility band power. But then to transform that into your cosmological temperature power spectrum, you actually use just this matrix, which takes into account of your UV sampling. So it takes account of the PSF, and it takes account into the primary beam attenuation. So this is also known as the window function in some sense. But here you just need to compute it once, and you check your binning and make sure your window function is largely diagonal, and it is quite efficient. And in the future, you can also try different baseline weighting and adding W projection kernel and different beams for different stations, so on and so forth, to further improve this pipeline while remaining sort of efficient and lightweight. Okay, enough of the setup. Let's just look at the results. To remind you again, this is very low redshift 0.3. So we're looking at very different angular scales, physical scales, comparing to EOR measurement. So here at the bottom left, you actually see the overall foreground power spectrum. Here in the center, you see the H1 power spectrum. So one thing to notice that at these really small scales, the majority of the foreground power actually comes from the point sources instead of the synchrotron. So point source really dominates here. And when you look at the ratio between your H1 power spectrum and your total foreground power spectrum, you find indeed there exists an observation window, but this window is much smaller than the ideal case, which is sometimes called the horizon limit. So this is maybe 10 times smaller than the horizon limit. So here the slope is 0.3, the horizon limit is probably an order of magnitude smaller. And I want to emphasize that although we do not model the anisotropy of the H1 power spectrum, actually this plays a huge effect at these small scales because you have the finger of God smoothing, right? So the majority of the information is going to come from these low K parallel scale, which is excluded by the foreground wedge, the foreground contamination. So this is sort of really bad news. But regardless, we can still have an observation window. We can measure the H1 power spectrum, and we try direct foreground avoidance to measure the power spectrum. So the blue line is the H1 only power spectrum, and then you have the results from the foreground contaminated power spectrum. You can see there's a slight overestimation, which is caused by the foreground leakage into the observation window. And if you try to do something such as the inverse noise covariance weighting, which further mixes your k-parallel scales, you can see the contamination gets even worse. So we really want to improve upon that, which calls for something. Which calls for something like the component separation method. So we annually bin the visibility data to construct empirical data covariance matrices. And then we use that to perform PCA to reconstruct our foreground covariance. So as you can see, the reconstructed foreground power spectrum agrees relatively well with the actual foreground. And we are able to enlarge the observation window to get to these low k-parallel modes that we wanted. And if you compare the results with the avoidance method, you can see that it is closer to the true H1 power spectrum. So, okay, the moral of the story is that visibility PCA is really good, but still we want to check, okay, can we do the more conventional thing, which is that we try to produce a radial image cube and then to measure the power spectrum. Because it's not the main focus, this is just a naive book. We're not trying to get back to the actual H1 input. We're just trying to match the image after PCA with the image of an H1 and noise only simulation. So the idea is that we produce using CASA, produce a dirty image which contains all the components, including thermal noise, and we try to do some PCA component separation. And as you can see, this is a very low thermal noise level, so you can actually see some bright H1 galaxies. Basically, all the features are recovered, but as you can see, for example, if you compare these two, there are actually some foreground residuals. So translating that to the power spectrum, you can see actually that most of the scales can be recovered by the image PCA. However, at the large scales, you're getting an overestimation. That is because at the shortest baselines, at the largest scales, synchrotron is actually having a much larger contribution. So the morphology of your foreground is a bit more complicated, so that you can't really resolve this with a simple PCA. And of course, that is also has something to do with the fact there is a PSF, there's a primary beam. So everything sort of entangled with each other. But anyway, so now it's for sort of real world thermal noise level. And this is just the forecast for our more simulation pipeline. So these error bars assume thermal noise level that's consistent with the entire MIT survey, which is ongoing and are producing some results. So for the entire MIT survey, we believe that H1 power spectrum can be measured with high accuracy. And remind you that this is very narrow redshifting. So we're able to probe the H1 evolution. And comparing different methods, we find that PCA invisibility is closest to truth. And as you can see, it produced the smallest error bars. So this is perhaps the method that should be further investigated. So this is my final slide, which is trying to improve our simulation pipeline to include more realistic instrument effects, more realistic beam. In terms of signal, we want to add in redshift space distortion, etc. And we will further look into our power spectrum estimation pipeline to include all the stuff that I mentioned earlier. Okay, yeah, that's me.
Thank you very much for your talk. So are there questions? I'm just checking questions and answers here in the Slack. So please also post later if you're now still pondering over your questions. So maybe in the meantime, I was wondering when you said at the beginning, with the example of LUFA, that it would be better to work in image space than in a UV space. Is this because of the calibration or systematics or like the pipelines we have, or why is that?
The honest answer is I don't know enough about this, but I think the most important issue is like your frequency resolution, which determines in terms of your redshift, which determines like how large your K-parallel can go, right? If you imagine you can go to like as high frequency resolution as possible, you can always try to avoid that the foreground. But if you have a low frequency resolution, obviously you're not going to get these high K-parallel modes, then perhaps you have to try to remove the foreground and suppress the wedge.
Okay, thank you. Is there another question so far? I don't see one.
I have a very quick one.
Oh, yes, sorry, I didn't see the hand. Yes, please.
Okay. Zhaoting, very, very good. I missed that, sorry, but what's the instrument that you assume? Is
So
it SKA law?
So it's Meerkat. So here we assume, sorry.
Meerkat, but as an interferometer.
Yeah, using Meerkat as the interferometer. This is actually sort of consistent with the ongoing MIGHTY survey. So this is like a realistic, how MIGHTY will see the sky.
Okay, so everything you said about the foreground removal, this K parallel, bigger than 0.3 K perpendicular is assuming this configuration.
Yes. So these will assume, the Meerkat beam, the typical PSF of 1 night of tracking. So yeah, and yeah, as far as I'm aware of, this is also consistent with what MIGHTY people are seeing.
Yes, thank you.
Cheers.
Okay, thanks a lot. So feel free to post further questions in Slack as always. And we go to the next talk now, which will be by Thomas Gessey-Jones. If you please could put up your slides.
Sure. Is that visible?
Yes, it's there. So please go ahead.
Brilliant. Thank you very much. And I'd also like to thank the organizers for giving me this opportunity to present my work. So yeah, I'm Thomas Gessey-Jones. I'm a second-year PhD student at the University of Cambridge. And what I want to share with you today is some work that I did over the first year of my PhD, which has resulted in this archive preprint draft with these co-authors. And this work was all about whether it's possible to use the cosmic dawn 21 centimeter signal to probe the first generation of stars, the so-called POP3 stars. Now, you've seen plenty of introductions to the 21 centimeter signal by this point in the conference, so I'm not going to go into too much detail, but the bit I would just want to draw your attention to for context is this falling arm that's going into the global signal absorption trough, which I've labeled here with the Wilson field effect. And this is commonly anticipated to occur due to the formation of the first stars. These stars form, they emit photons in the Lyman band. These cascade or redshift into the Lyman alpha, and this produces the Wilson field effect, coupling the gas temperature and the spin temperature of the IGM, producing this deeper global signal. And so it's immediately apparent that in our anticipations for the global 21 centimeter signal and also the power spectrum, that the first stars and their formation is anticipated to be an important part of predicting the signal, and therefore also an important part of simulating it. But these aren't the only impacts that these first stars have. These same Lyman band photons that produce the Wilson field effect also allow these first stars to heat the gas, both directly and indirectly via C&B heating. They can also change the chemical composition of the IGM via the Lyman-Werder feedback, and also along with their and higher band UV photons can ionize the gas. Furthermore, these stars, when they die, can ionize and heat the gas via their supernovae, enrich the IGM, provide additional heating through their XRBs, and also, as Anastasia mentioned in her talk earlier, potentially provide an excess radio background. So these first generation of stars have a wide range of impacts on the IGM and thus the 21 centimeter signal, some of which are anticipated to be quite significant. But with all that being said, our knowledge of the first stars isn't that well fleshed out. Taking, for example, their mass distribution, the initial mass function, simulations have yet to converge on predictions for this, though they're making good progress in that way, while our experimental bounds on the mass distribution of these first stars are 2 orders of magnitude apart, and there are caveats to both of these that mean that they may be weaker than they are depicted here, with no direct measurements of the IMF yet. So we have a wide range of possible mass distributions that these first stars could still possibly have. And so this was the kind of the initial motivation that got us looking into this area as to, well, if we have an uncertainty in the properties of this first star, say their mass distribution, the IMF, how does that propagate through uncertainties into their emission properties, into the Wilson field effect and the gas temperature, and finally into the 21 centimeter signal? But this propagation of uncertainties is a double-edged sword. Yes, it might mean our theoretical predictions are less certain, but it also means if there is a dependence of the 21 centimeter signal on the POP3 IMF, then we could, reverse this around and think, can we use the 21 centimeter signal to probe the IMF? Which I guess is the more optimistic outlook on this work. Now, the other, as a side effect of this, we wanted to ensure that we were modeling the POP3 stars in our semi-numerical simulation as accurately as possible. So we also, as a secondary goal of this work, tried to reevaluate a couple of assumptions that had previously been used in semi-numerical simulations. I'll get to more detail later on. So we can't, for now, we're not going to look at all 9 of these effects. There's a lot of things to be done. Instead, we're just going to concentrate on the Lyman band effects. So this is the Wilson field effect, the Lyman and CMB heating, and the Lyman-Werner feedback. These were chosen mainly due to the fact that the Wilson field effect is this dominant effect creating the cosmic dawn power spectrum peak, and the global signal absorption trough. And so these effects clearly have dramatic impacts on the cosmic dawn 21 centimeter signal at high redshifts. The other effects are anticipated to potentially be important, but particularly say the X-ray heating and ionization, but these go into lower redshifts towards the epoch of reionization. So while we are talking about IMS, I think we should mention all this work that's been done has been done such that you could use an arbitrary IMF, but in this actual work and in this talk, we'll use a couple of fiducial IMFs just to kind of guide our discussion. And these are the Salpeter IMF, which is like the IMF seen today, and so is dominated by low mass stars. An extremely top-heavy IMF, where all of the stars are basically above 300 solar masses, which is more in line with early 2000s theoretical expectations, but sort of seems to contradict simulation results that are more recent. And then a couple of intermediate IMFs between these two extremes to sort of allow us to span the range of possible 21 centimeter signals from different IMFs. Now, I've been talking all about IMFs, but obviously the IMF is a population level statistic. And before I can go into predict the Lyman band emission from a population, I need to consider the Lyman band emission from individual POP3 stars. And this formed a large part of the actual work on this project, was modeling initially the stellar evolution for individual POP3 stars over 3 orders of magnitude of mass, and then combining these stellar evolution tracks that were computed using NISA with the stellar atmosphere code TLUSTY to predict the spectra of the star at each point in their lives, and therefore their lifetime emission in the Lyman band of these stars, as well as their emission rates at various points. This then produces a data set of Lyman band emission spectra for individual POP3 stars that we can integrate over in our semi-numerical simulations to find the population level for a given IMF. Now, before we sort of start comparing IMFs, though, we should double check that these assumptions that are being made in these simulations are valid. And in particular, 2 assumptions we looked at were found to be somewhat problematic. So the first was that the previous assumption that the data sets we're using were that the spectra for the stars that were being used was just their zero-age main sequence spectra. And it was implicitly assumed that this zero-age main sequence spectra for the stars was the same as their average spectra. Now, this was found to not be true, at least in the Lyman band for these, for POP3 stars. Their Lyman band emission typically increased over their lives. And so this zero-age main sequence emission assumption led to an underestimate in the Lyman band emission efficiency of POP3 stars. And consequently, the Wilson field effect was delayed, and the 21 centimeter signal was erroneously shifted by about 2 redshift to lower redshifts to later times. This, with our suite of full stellar evolution simulations, we were able to relax and find a more accurate model. The other assumption that was problematic in some cases was whether in the actual simulation itself, we can ignore the fact that the stars have finite lifetimes and just model their emission as instantaneous. And as long as you're using one of those top-heavy IMFs that I talked about, where the stars are above, say, most of the mass in stars is above 20 solar masses, actually it's fine. These stars are quite short-lived on cosmological timescales. But if you go to an IMF like the Salpeter, where the star mass is typically below 10 solar masses, these stars live for hundreds of millions of years, which is not an insignificant period of time. And consequently, again, what happens is the Lyman band radiation field in this case is overestimated by assuming that these stars' emission is instantaneous. And so again, you see this erroneous shift in the 21 centimeter signal. So we extended our semi-numerical simulation to allow for the finite lifetime of these stars to be properly modeled. Now we know which assumptions we can and can't make. We went ahead and can compare the 21 centimeter signals predicted for our different IMFs. So just initially comparing our extremal cases of the Salpeter and the top heavy, we can see that there are differences in the 21 centimeter signal predicted between IMFs. And these differences in the global signal are comparable to the edges residuals, reaching 30 millikelvin. And the power spectrum differences, which are mainly in high redshift 22 to 35 regime, were found to be larger than anticipated sensitivity of SKA1. So in theory, the difference between these two IMFs is within a measurable range. But when we look actually at the other two IMFs, the log flat and the intermediate, they seem to basically match the top heavy. And it was something that we found in general, that IMFs where the majority of the solar mass was in the higher mass stars all seem to produce more or less the same 21 centimeter signal, sort of a generic high mass solution. Returning just quickly to the variations between the extremal IMFs, though, these differences could not be eliminated by altering the star formation efficiency. So it does seem that there are signatures in the 21 centimeter signal which are down to IMF and not just the multiplication of the Lyman band emission efficiency and the star formation rate. So when does this generic high mass solution appear? Basically, when does the 21 centimeter signal become insensitive to the IMF of the POP3 stars? And by considering a simplified case that we take all the POP3 stars, they're the same mass, and we're just going to vary that mass and see how the 21 centimeter signal varies. We can see that in the global signal, variations are seen from about 10 solar masses, and the power spectrum from about 20 solar masses. So kind of clearly above this 20 solar mass threshold, at least in these statistics, it appears that the 21 centimeter signal is fairly insensitive to the IMF. As I'm coming to the end of my time, I'll just quickly wrap up with my conclusions. So we evaluated a couple of assumptions, whether the stellar emission over the star's lifetime can be taken as just its zero-age main sequence emission, and whether POP3 stars emission in semi-numerical simulations can be taken as instantaneous. And we found in some cases these are not. These simulations can't. These assumptions cause erroneous predictions from the simulations. And then looking at comparisons of the 21 centimeter signal predicted for different IMFs, we find that if the IMF is below 20 solar mass, is dominated, by stars below 20 solar masses, then yes, we could potentially use the 21 centimeter signal to probe the POP3 IMF, while instead, if it's the potentially more likely case of it being dominated by stars above 20 solar masses, then it seems that all the 21 centimeter signal can do is provide a lower bound on the characteristic mass of the IMF. However, all this work comes with the caveat that we've only considered 3 of those 9 effects so far. And it's possible that the introduction of other ones will kind of break this high mass degeneracy and make the 21 centimeter signal an even better probe of the POP3 IMF. So just in the final few seconds, here again is the archive link. And we've also made all the sort of Lyman band emission spectra data available on this Zenodo repository. And hopefully I haven't overrun too much so that there should be a few minutes left for questions.
Thank you. Yeah. So we have time for questions. So great. Please post on Slack. I don't see one on Slack yet. And also you can put questions and answers here if you're not on Slack. But in the meantime, while people are thinking and typing on Slack, so I was wondering, is there hints at if like a more top or bottom heavy IMF might be better for what we start to have in constraints?
So the theoretical expectation, I think, is that it's going to be fairly top heavy because you don't have as efficient fragmentation in POP3 star formation as you do in POP1 and POP2 star formation because you don't have the metals for efficient cooling. There is simulations seem to be the initial sort of simulation results seem to be suggesting something more in line with this log flat one that I mentioned, where sort of when you view it as instead of the number of stars per unit mass, the number of stars per unit log mass, it's a flat spectrum. So there's a few papers which have given samples of at least protostars that seem to be obeying a sort of log flat distribution, but I think the different simulations, as far as I am aware, haven't converged yet to like an agreed upon expected IMF.
Okay, thank you. We got one on Slack as well. So I will just read it by Stefan Erich. Very nice talk regarding the caveat. How do you expect the signal to be affected if the variation of X-ray heating with the POP3 IMF is included?
The X-ray heating is probably the most complex of them because the X-ray heating depends on the X-ray binaries. And this isn't just a simple case of, you take the X-ray from each star and you integrate over it. It's going to depend on things such as, the eccentricity distribution of the binaries that form, and sort of you need actual binaries with differences in mass. So you need a star that forms a black hole, but then you also need another star that's sufficiently more long-lived than that to provide it with matter. So how it's actually going to vary with IMF, I don't really have a good intuition for. I think it's going to be fairly complex. Some initial results from Nina, the kind of second author on this paper, suggests is that sort of the intermediate IMFs are more efficient at producing X-rays and so have greater X-ray heating. But I'm not sure if those results are on archive yet. So if they are, I will send a link to the Slack.
Okay, thank you very much. And so the Slack is as always open still. And we go to the last talk of today's session by Joe Lewis. I see your slides are getting on.
Hi, everyone.
Hi, it's not full screen.
Here we go. So hi, everyone. I'm Joe Lewis, a postdoc out of Heidelberg. And today I have a lofty talk title for you, which is the signature of galaxy formation models as viewed by the 21 centimeter signal during reionization. So at this stage, I've taken the liberty of forgoing like the classical introduction slide with the reionization timeline, and I've gone straight into motivations. And so I think in this conference, we're acutely aware that a lot of really interesting work has gone on to try and understand what the interpretations are of the current sensitivity of our instruments with respect to the 21 centimeter signal, but also what the interpretation of the one-day detections might be. And so one of the very popular methods has been to use semi-analytical models, as they allow you to explore really huge grids of various astrophysical parameters. And so I'm today interested in one particular, I think, typical feature of these, which is that generally galaxies are painted onto halos in some way. And so the way in these approaches that you account for different assumptions about feedback, so AGN feedback or stellar feedback, and star formation are all kind of merged down into the relationship between halo mass and stellar mass. So you kind of govern the slope and the value of particular halo masses to incorporate for these ideas about feedback. And so the question I want to ask is, can we find something different or extra? Because this approach, as in 21 centimeter fast, is probably sufficient to capture the main differences. I think everyone agrees with that. But can we find some lower order differences that might still yet be important for our interpretation of the signal? And so to do that, the proposition is to use some of these big galaxy formation simulations that are just, hanging around on hard drives, not some of them not doing much. Okay, so I don't think the approach is going to surprise many of you. I assume a very, very classic expression for the brightness temperature. And so the kind of handy thing about this expression, which I guess is why everyone uses it and abuses it, is that you can just decompose it very easily as the product of, being proportional to the product of the various physical components that interest you for the signal. And so most of these can come straight from the simulations that I'm using, which are Illustris TNG, and the Eagle simulations. But there are some extra assumptions required because, in fact, these simulations weren't actually intended to be used for reionization studies, or at least that was not their focus. So I need to do something to work out, to post-process them, to understand how reionization happens in these boxes. And a further little point here is that for the same reasons, though it doesn't make incorporating the physical effects from the spin temperature and the gas temperature impossible, for now, starting from the simple end of things, I've placed myself in a redshift time frame where the temperature term is basically 1 and the temperature effect is subdominant. So if I were to make a very basic sketch of what the pipeline is, I'm taking my 4 simulations, which are again TNG, Illustris, Eagle, and I have a model variant run of TNG, which I'll get back to a bit later. And I'm taking their star formation, turning it into source fields of ionizing photons using BPAS binary SEDs. And then I'm applying some typical assumptions about what the unresolved escape fraction might be. This, along with the gas density in the various simulations, I can then plug into a code called SciFog, written by Ann Hutter, that uses excursion set formalism to determine the neutral fraction in these simulations for my various assumptions. And so I can then just use that along with the other remaining simulation properties and compute the brightness temperature. So if I can take you swiftly to maybe the interesting part, I'd like you to take you on a tour of the various things I've been looking at. And this is just a quick map of the brightness temperature in TNG at a redshift of 6.5. So first up on our tour is something already a bit more quantitative, and it's the mean evolution of the brightness temperature in TNG, Illustris, and Eagle. On the right here is a function of redshift. And so what I'm showing you, the diamonds represent the fiducial model that I've retained. So this includes assumptions about the escape fractions and the velocity effects, so the redshift space distortions. But the shaded areas are showing you the minimum and maximum values for each simulation that I obtain when I turn on and off or switch between all these assumptions, right? So across the board, it's relatively in the same waters, but you'll notice that the Illustris simulation has a much higher mean brightness temperature towards the end of the window I'm looking at, towards a redshift of 6. And so this is mainly down to the different reionization history, as in Illustris it ends a bit later. So another way of looking at things that we've already seen, of course, is looking at the power spectra. And again, here the picture is kind of similar in a way because the results are close, but Illustris seems to distinguish itself here in the smaller scales that I'm representing, where it has more power. So one of the maybe different ways of looking at the power spectra to make such a comparison is to try and account for differences that are solely due to the timing of reionization, okay, and try and only look at the ones that are due to the topology differences. A way of doing that, roughly, is to, instead of looking at the power spectra at fixed redshifts, look at them at redshifts where the mean neutral fraction is similar, which is taken as representative of the advancement of reionization in the box, and so the stage of reionization that you're representing. And so you can see 2 or 3 things have happened here to the power spectra that I've been showing. First, the bands, the shaded areas are much smaller. This is because the primary source of their width in the previous plot was down to the different assumptions about the sources. Okay, so when you account for timing, which is the main driver of the differences you're seeing here between models, they're actually a bit thinner. And you see now that actually the comparison between the simulations yields something a bit different. So you see differences across many different scales now. There are differences at the larger scales, in the intermediate scales. The interesting thing is that Illustris remains, still has more power at these smaller scales even when we do this. So maybe there's something extra going on here. I'm afraid I might be really speeding through this, but let's take you to it. So I've chosen to show you what I find the most interesting, okay, when you look under the hood here. And so I've represented the power spectra of one of the main components of the brightness temperature signal, which is the power spectrum of the matter density of the simulations. And so this is on the right here as a function of scales at a given redshift. And there's actually an extra curve in here, which is called TNG 100 1NR. And so this is a special run with the same setup as TNG, but in which cooling, star formation, and feedback were actually turned off. So basically you have gas and dark matter subjected to gravity, and that's it. And so the really striking thing is when you look at the small scales of these matter power spectra, the Illustris result is actually closer to the gravity-only TNG run than it is to the TNG run or the Eagle run. And so this is even more striking if you consider the fact that so TNG and TNG 1NR and Illustris actually share initial conditions. And one of the main changes between Illustris and TNG was to substantially increase the potency of stellar feedback at early times so as to better match the cosmic star formation density. Yeah, and so this is under investigation still about how this all plugs in and how we can explain this. And prove it more definitely. But yeah, I think I have gone really, really fast. I did actually budget the time for this properly, but stress, I guess. And so this leads me to my takeaway points, which I could read out, but I guess I prefer to leave more time for feedback and questions, if that's okay.
Sure, yes. So thank you very much for the talk. I'm just checking quickly on Slack if there's already a question or if here's a question and answers. Not yet. So please post on Slack and questions and answers. Or the panelists can also ping me to speak up if they want to. In the meantime, I was wondering, so you said you're basically working in the post-heating regime, neglecting the spin temperature and also the gas temperature, the kinetic one, if I understood correctly.
What I mean, the gas temperature is part of the spin temperature in a way. That's what I mean.
Yeah, so basically when you're going from from the hydro to the 21 centimeter brightness temperature. So okay, so then I was wondering, do you have a feeling of how large the difference will be in your maps, and what would be your steps to include this? I mean, one could go fully radiative transfer, or maybe try a simplified route.
Yeah, so the worry about the simplified route would be that it would be difficult to actually argue that we're seeing something proper that's an effect, I would think. So the next steps are to look towards a full radiative transfer post-processing of these boxes. There's a student working in our group on a new radiative transfer method that we intend to apply.
Okay, thanks a lot. So we actually have questions pouring in on Slack. So I'll start with the first one by Fräulein. Hi, Julius. Can you remind me how much the UVLF predictions differ between these simulations? Meaning, could some of the differences be reduced if simulations were retuned to better agree with current observations?
Can you, so what observation, sorry?
The current, I think just generally. So the first bit of the question was how much the UVLF predictions differ between the simulations.
Okay. Sorry, I didn't catch that. So yeah, it's a good question. So I think a lot of these simulations were not designed to address reionization. So they have focused on the lower redshift constraints on the luminosity function. However, I know that I think TNG is a relatively good match to the luminosity function out to redshifts of 5. I'm not sure if everyone has looked. I've looked a bit at this, but I can tell you that I showed you the results, but the kind of analysis, some of it I didn't have the time to include. And so it's very interesting if you look at the different source populations of the simulations, because the galaxies that are reionizing the universe are quite different in these different simulations. So I think it's really intriguing to that's how I'm approaching this kind of project. Is it's a way of trying to merge the communities of people who look at low redshift galaxies and what I've been doing so far. I hope that helps a bit. There'll probably be luminosity functions in the paper.
I mean, so the question is also on Slack, so you can elaborate more then later if you want to. Maybe, he's also writing, yeah, thanks, that's interesting, he got it. So maybe very quickly by Gerald, and before we conclude, great to see these results. Are the power spectra at those small scales reliable? Wouldn't they be sensitive to aliasing?
So this is something we've explored by making, so in this process, I don't compute the power spectra straight off the repo Voronoi cells from these, for example, from TNG. I resample it onto a grid. And so I've explored using different resolution setups. And I agree that this is the area that would be the most sensitive to numerical effects from computing the power spectrum, but it appears to be relatively stable. And if you still have doubts, I'd argue that whatever's going on, there's something there because I'm applying the same process to these simulations in an equal manner. And there's definitely something there.
Okay, thanks for the reply. And that one is also on Slack. We have one more on Slack, but I think I would ask you to discuss this one on Slack as well. It's on the low mass or star formation being resolved by Stefan Erich. So thank you very much for your talk. And again, thank you very much also to all the speakers of this session today. And of course, also all the participants that made it lively. And we will come back tomorrow with our conference at 500 GMT with a session on cross correlations. If there's anything else by the organizers, by the SOC.
No, that's great. And thanks to you, Caroline, for chairing the session.
Thanks a lot to you for this conference. But well, it's continuing tomorrow. So see you then. And yeah, thanks again to everybody.